In this unit, we'll look at membrane filtration for both water and wastewater treatment. So when we talk about membrane filtration, we talk about basically four types. And those four types are reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. We can think of reverse osmosis and nanofiltration as pressure-driven, and we can group ultrafiltration and microfiltration as sieving. There's overlap between those two, and all of these, except microfiltration, require significant pressures, but we can essentially divide it up in that way. Now, all of these involve the use of a semi-permeable membrane. That membrane is permeable to water, and as you'll see, some other substances depending on the membrane type. And the rate of passage of water and also solvents really depend on pressure, the concentration of those solvents, those solutes in the solution, and then temperature. So pressure, concentration, and temperature are the major controlling factors, along with the properties of the membrane itself. So I'm going to play a short video, and this demonstrates the issue or the concept of semi-permeable membranes.
One we'll use as our control. The second one we'll put in a beaker of water. 2 hours later, let's see what our results are. You can see definite change in the volumes. And if we move this around, you can see that in this larger volume, the molasses is not nearly as viscous. So we have plenty of evidence to support the fact that the water molecules move through the dialysis tubing and it's diluted the molasses.
Okay, so this is just a shortened video. The entire video link is at the bottom of the image. Basically, what was done here was to take dialysis tubing and in that place molasses in the dialysis tubing. You see the first, the control, which is just the molasses in the dialysis tubing, and then the other showing the dialysis tubing after it sat in water for about 2 hours. So what you see is that the water or the membrane is permeable to water, so it allows water to pass into the membrane. The sugar molecules aren't able to pass out of the membrane, and then what you see is that the molasses becomes more dilute. So it tries to give you a sense of what we're talking about when we're talking about semi-permeable membranes. So membrane processes are extremely effective. We'll talk about in the next couple slides. They're effective at removing a variety of contaminants depending on the type of membrane we're using. The problem is that the rate of water flow across the membrane is slow. So we need a large membrane area, and that presents some significant challenges. Now, we can use this, though, to separate colloidal and dissolved solids that we couldn't separate effectively by either sedimentation or by granular media filtration. The disadvantage is that there is a high pressure drop across the membrane surface, and that means that the system requires a high amount of energy input. This figure here shows the different types of membranes. And as I've mentioned, we have microfiltration, ultrafiltration and nanofiltration, and then reverse osmosis. So in terms of pressure, microfiltration is operating at about, think of it at about 1 atmosphere, okay? Or less than 14.5 psi. As we decrease the pore sizes here, we increase the pressure required across the membrane surface. So we're talking here about 14 to about 150 psi. Here we're talking about 300 to 600 psi, and here 600, about 600 to, and this isn't exact, but to about 900 psi, just to give you an indication. So again, as we decrease the pore size of the membrane, we're increasing the pressure that's required. Now, in terms of removal, you see here, what we're removing is predominantly bacteria and fats. So, for example, microfiltration can be used to remove bacteria. It can also be used to remove cryptosporidium and giardia. It can also be used in some industries, for example, in the production of skim milk, because it will remove the fats from milk. We move to ultrafiltration, and now we're starting to remove proteins. We're going to remove bacteria, cryptosporidium, oocysts. Pressure is increasing, but we can remove more of the contaminants. We can also remove some viruses. Now, when we move to nanofiltration, now we're removing, again, smaller molecules. We can remove essentially all viruses. So we will remove the bacteria, we'll remove crypto, and then almost all, or essentially all, viruses. And then when we're looking at reverse osmosis, now we're looking at removing ions. So when we're looking at desalination, so removing of the salts from seawater, we're looking at reverse osmosis. We may be able to get some removal of these same ions with a tight nanofiltration. You can see there's some overlap in terms of both the pore diameter and also in terms of the pressures that are used. This is just another image to, again, show you what we're removing. So we've talked about granular media filtration. So when we're looking at, for instance, sand filtration, we're looking at removing particles in this range. We can remove algae. We can remove cysts and oocysts, so giardia and cryptosporidium. We can remove most bacteria. And in fact, we'll get some additional removal because of just attachment. When we're looking at microfiltration, we're now removing essentially all of the bacteria. To remove viruses, we need to move to ultrafiltration. We can remove organics, and this really depends on the molecular weight at tight ultrafiltration membranes. And then we're looking down at nanofiltration and reverse osmosis to remove dissolved ions. So this kind of gives you a range, both in terms of molecular weight of the compounds that we're removing, and then the pore size of these membranes. Now, when we talk about reverse osmosis, the way osmosis works is that it's the net movement by diffusion of a solvent from a region of higher water concentration to a region of lower water concentration. So you can see here, we have a higher concentration of, let's just say, sodium chloride. And then we have a lower concentration on the other side of the membrane. You saw that with the molasses experiment, except in that case, it would be sugar. So what happens? The water moves across the membrane. The ions in this case are unable to move across the membrane, so we end up with a more concentrated solution on one side and a less concentrated solution on the other. And the attempt is to show that you can see that the water level changes because water is moving across the membrane. Now with reverse osmosis, what we attempt to do is the opposite. So we apply a pressure here. We're pushing water across the membrane. This becomes our permeate. This is what we're producing. And then what doesn't pass through the membrane becomes our reject stream. So we have two streams that we start with one. We produce a permeate stream, and this is our product stream. And then we have a reject stream that has the higher concentration of whatever we're attempting to remove. To give you an idea of the differential energy cost, here is conventional surface treatment. So this is just energy costs in kilowatt hours per cubic meter of water produced. With desalination, we're typically treating water that has about 35,000 milligrams per liter of TDS. For water reuse, we're looking typically at waters that contain about less than 1,000 milligrams per liter of TDS. Now, when we talk about water reuse, often what we're talking about is what we call intended water reuse. So we take wastewater effluent, we're passing that through ultrafiltration and RO, and we're producing water that could be used for potable water. That's the whole idea. So what is unintended water reuse? So this is unintended water reuse. We're recycling wastewater effluent and then using it for drinking water. It's used in areas where water is scarce. So you'll see it used, for instance, in Israel. Singapore recycles a portion of their wastewater effluent. So what's unintended water reuse? You have the East Lansing wastewater treatment plant. Where does the effluent go? That
Into
scavenger
the Red
hunt?
Cedar.
To the Red Cedar. And where does the Red Cedar go?
Does that go to Grand River?
Mm-hmm. Where does the Grand River go?
Lake Michigan.
Lake Michigan. And who uses Lake Michigan water for drinking water?
Some West Coast cities.
Yep.
In Michigan.
Grand Rapids, Muskegon, basically Holland, pretty much the entire west side of the state. And then Chicago, Milwaukee, anything along the the west side of Lake Michigan. That is unintended water reuse. I used to have a t-shirt that said we all live downstream. If you think about it, in effect, we all do. Anyone that's using surface water, we're recycling the water that we have in the hydrosphere. So that's unintended water reuse. Intended water reuse is when we actually plan to use the wastewater effluent for potable water. Any questions about this? So you can see, in terms of cost, it's a lot more costly from an energy perspective to desalinate water than it is to reuse water. And then vapor distillations is extremely expensive, which is why we don't use vapor distillation on a large scale for water treatment. It's just orders of magnitude more costly than either conventional surface water treatment, desalination, or water reuse. Now, in terms of the cost of desalination, a significant cost is electricity. Another significant cost are consumables. This will include replacement of membranes. Typically, you're replacing polymeric membranes about every 3 to 5 years. In terms, this here is more of the actual housing for the membranes. It also includes chemical costs. As we talk about, there's often chemical pre-treatment and post-treatment that we need. Cleaning of the membranes, we'll talk about fouling. So all that would be in consumables, and then just in spare parts, investment costs. Staffing to run the plant is actually relatively small. It's only about 1%. Running the plants are not a significant cost in terms of a desalination plant. Membrane replacements, consumables such as chemicals, and electricity are your major costs. Now, you'll also hear about forward osmosis. This is an attempt to get around the pressure issues or requirements on a membrane, on a regular reverse osmosis membrane. So instead of applying pressure, what they're doing is they're using a concentration gradient. So they're using a high concentration, in this case shown here, of sodium chloride. And that concentration is what's driving reverse osmosis.
Percent of dissolved impurities, but is super thin so H2O can easily pass through. Just as impressive, Oasis uses a highly concentrated salt solution to draw clean water across the membrane without using energy-hungry high-pressure pumps. The water and draw solution are then separated using low-grade heat or a secondary membrane. The draw solution returns to the system in a continuous process, leaving fresh water ready for industrial use or human consumption.
So you can see in this video, a portion of the video, is that, again, what they're doing is they're using a high concentration brine solution to create that concentration gradient in order to drive water across the membrane. You still have your reject stream. And then what they're doing is, shown here, is with a secondary membrane. So here, this is the reject stream from the secondary membrane. This is the product stream here. So this is the clean water that would then be used. The advantage of this is, you can see kind of by the color, that if you have, and we'll talk about fouling, removal of this organic material, removal of bacteria, that would occur here. So this is the reject stream. Water passes across here, and then what we're going to do is we reconcentrate here the salts, and then we're going to use this gradient again. And so essentially it's a dual loop membrane. Now the flux of water across the membrane can be described by this equation here. So the flux, notice here, is either in kilomoles per second per area. So this is the area of the membrane, really a specific flux. And here we have it as a volumetric. So it can either be as mass per second or it can be as volume per second. And it's dependent on this coefficient of water permeation, which is dependent on the membrane. And notice here, this is dependent also, it's your flow divided by the surface area of the membrane times the pressure. So it's a specific coefficient, really. It's, since we've included pressure, dependent on the pressure. And it's that flux is dependent on what we refer to as the transmembrane pressure. That's the pressure difference across the membrane surface. This is transmembrane pressure. And this is the difference in the osmotic pressure in the across the membrane surface. So we're both looking at across the membrane surface. This is the pressure, the transmembrane pressure. So it's difference in the pressure across that membrane. And this is the difference in the osmotic pressure between your feed solution and the permeate. The solute flux is the flux of salt or other chemicals that pass across the membrane surface. So for instance, if we're looking at that sodium chloride solution and we have a membrane surface, so here's our membrane, we'll take seawater, we produce a product stream and a reject. That product stream will have some salt in it. Perhaps we have 99, what we refer to as 99% rejection. That means if we start at 35,000 milligrams per liter, how much salt is in the product water?
1% of that.
1% of that. So 350 milligrams per liter of salt, or sodium chloride. So some of the salt will pass across that membrane. It's not 100% removal. And what this equation here shows you, one, it's dependent on the difference in concentration across that membrane surface. It's also a function of the membrane itself. So different membranes will have different mass transfer coefficients or different removals of your salts. Now, it's dependent on the diffusivity, which describes the rate of diffusion of that chemical. The higher the molecular weight, the lower the diffusivity. The chemical is not going to diffuse either in air or water as rapidly if it's a higher molecular weight. As temperature increases, the rate of diffusivity increases. So if this is true, as molecular weight increases, diffusivity decreases, and how does the flux of salt change? If we're looking at salts having a higher molecular weight, so for instance, we could look at chloride, we can look at bromide. Which one has the highest molecular weight?
The bromide?
The bromide. Okay. So if that has the highest molecular weight, diffusivity decreases. So how does the flux change?
Would it decrease?
It'll decrease because it's proportional. So your flux is proportional to the diffusivity. On the other hand, if the temperature increases, if we just look at chloride, as the temperature increases, diffusivity increases. So now what happens to the flux for that same salt? So if temperature increases, as temperature increases, my diffusivity increases, what happens to the flux? Exactly. Okay, the flux will increase. Which means what? Why is this important?
Would we want to run the desalination plant at a colder temperature?
Exactly. So, or for instance, if you're looking at wastewater, during the summer when the temperature is higher, you'll have more salt in your permeate stream because the diffusivity is greater. It also means that in terms of designing, you need to design, if you want a certain removal, you need to design for the highest temperature. You'll get better removal in winter, but that's your controlling temperature. That's your controlling situation, is the high temperature. So you design for the high temperature in terms of the solute flux, and then you have better removal in winter. We also talk about recovery. When we talk about recovery, we're talking about the water. So for instance, we have a water stream and we have a pump, and then that water flows, passes through a membrane. A certain portion of it will be our product stream, and a certain portion of is the reject stream. So in this case, let's say we produce 75%. So that means 75% of the feed is product water or permeate. 25% of that flow is reject stream. And this we have to dispose of. We'll talk about disposal on Wednesday. When we talk about rejection, we're talking about the salt. And I mentioned that before when I said 99% rejection. So there we're looking, as I mentioned, with feed. So let's say we start at 35,000 milligrams per liter. If we have 99% rejection, we have 350 milligrams per liter in our product water. Now, the other terminology that's used is this terminology about arrays. So we have feed water. We have product water that we're producing. So this is our product water here. We have our reject stream. And what we're doing here is we're taking that reject stream and we're passing that through a second membrane system. Again, we have a reject stream here, and we have a product stream here. This is referred to as a 2-by-1 array. So we have 2 stages here, followed by 1 stage here. Why would we do this?
We make the first stage like a larger pore size, and then the second stage a smaller pore size.
We could do that. So we could change the pore size. Okay, we also, typically your stage 1 is going to have more membrane units on it. So you're basically squeezing out as much water as you can reasonably do for this type of a situation, okay, for that conditioned water. And then what you're going to do is you're going to take the reject stream. You'll have a smaller membrane unit there, and you're going to try and essentially squeeze out more water. So you're basically trying to produce as much water as you possibly can from that feed stream. This is an example of a system in Sydney. I'm only going to play a portion of the video.
The St. Mary's Water Recycling Plant uses reverse osmosis to further treat wastewater after the ultrafiltration process. Reverse osmosis membranes are constructed from a membrane flat sheet. It is comprised of 3 layers: a polyester fabric support base, a microporous polysulfone layer, and a 0.2 micron thick polyamide barrier layer. The polysulfone layer strengthens the very thin barrier layer. It is the barrier layer that removes nutrients, chemicals, bacteria, and viruses from the water. The membrane flat sheet is combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets for the feed water. A sheet of permeate spacer is added to the membrane sheets and feed channel spacer. This enables the final recycled water product, or permeate, to flow evenly across the entire membrane surface, even under high pressure. The back of the membrane is completely sealed to the edges of the permeate spacer. The membrane sheets are glued along each of the 3 exposed sides and rolled around the core tube. Feed water is forced through the feed channel spacer and into the barrier layer of the membrane. Water passes through the membrane surface into the permeate channel. It flows in a spiral direction and collects in the core tube. This water is the final recycled water product, or permeate. There are 7 spiral wound elements loaded in one pressure vessel. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced. Feed water is pumped at high pressure into the vessel. As it travels, small molecules like water pass through the membrane, while larger particles such as salt, bacteria, and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water. At St. Mary's, there are 6 reverse osmosis treatment trains, each with 3 stages. This design produces the highest amount of recycled water with reduced concentrate waste. Stage 1 has 52 pressure vessels, Stage 2 has 24 pressure vessels, and Stage 3 has 12 pressure vessels. 58 million litres of feed water enters the reverse osmosis system on a daily basis. As the feed water passes through each stage, more recycled water is extracted. 65% of recycled water is extracted at Stage 1. The remaining 35% is passed through Stage 2, where a further 10% is extracted. The final 25% is passed through Stage 3, where the last 5% of recycled water is extracted. 80% of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St. Mary's. The remaining concentrate contains so much salt and impurities that to recycle it would not make economic sense. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant, where it is treated and released into the ocean.
We'll end there, but I just wanted you to have a sense of what a treatment system really looks like. Notice here, they've used 3 stages to try and achieve as much product water as they possibly can. And notice the number of units. So they've got 52 in the first with 6 membrane elements in each of these vessels in order to produce the requisite amount of water. What we're looking at now is just how membranes, and these typically are spiral wound membranes, and how they are organized into a membrane system. And what you see here, and let's just look at the end perspective. And what you see are, again, light granular filtration membranes. Notice that the plumbing is such that you have, for each membrane unit, you've got these two membranes plumbed like this. Again, it's just cheaper to plumb these membranes. The piping is expensive. So if we can minimize piping, we want to do so. So what you see is basically there's 4 banks of membranes. We have six membrane vessels. So each one of these units here, or you can see it here, is known as a pressure vessel. And in the pressure vessel are your membrane elements. So the way this is set up is this is referred to as a 4x2 stage arrangement. So we have 4 banks, 1, 2, 3, 4 banks of membranes. We have 6 membranes, pressure vessels per bank. So we have 24 vessels. That's where the 24 vessels comes in. So that's for stage 1. In each pressure vessel are 6 elements. So that's 24 times 6 equals 144. So there's 144 membrane elements in stage 1. And then stage 2 has 12 vessels. So we have 2 banks, each with 6 pressure vessels. Again, we have 12 vessels. We have 6 elements per vessel, and that gives us the 72 elements. We can also describe it with the schematic that's shown here. So what we have these, think of these as the 4 banks. We produce, switch to, so this is our product water here. So we're combining all of this product water or a permeate, and we have permeate from the second stage here. And then we have a reject stream. So here is the reject stream. And that reject stream is then passed through stage 2. We still produce a reject stream or a concentrate that has to be disposed of. The last one here is a 4x2x1. So the only difference now is we would take the concentrate or the reject stream here, and we would put that through another vessel. We would again produce reject stream, and then we have permeate that we could then add. What we're kind of think of it this way, that what we're trying to do is squeeze out as much product water as we possibly can, so that we're producing the greatest percentage of that product water. We're minimizing the flow of our reject stream. Now, this means that the reject stream becomes more and more concentrated, which also becomes a challenge. I'm going to play this as a short video. I edited this morning just to try and give you a little bit greater sense of how water is flowing through these membranes.
Feed enters at one circular end of the spiral membrane and travels down the membrane here, illustrated by the red arrows. Permeate, illustrated by the yellow arrows, and retentate, illustrated by the dark red arrows, leave at the other end of the spiral membrane. As the feed travels down the spiral, it becomes more concentrated, illustrated by the increasingly deep red color of the arrows. This concentration effect is due to the fact that the transmembrane pressure, that is, the difference in pressure between the feed and the permeate side, induces a flow of permeate through the membrane layer. The membrane is constructed such that the permeate is transferred to a perforated central tube known as the permeate tube from which it leaves. It may be easier to understand how this separation takes place by unrolling the spiral membrane, allowing a further look at the membrane construction. The feed can only enter where indicated since the membrane sheets are glued to form membrane envelopes that contain a spacer which ensures that the permeate is transported to the central tube. The spiral module is constructed by attaching a number of properly glued membrane envelopes to the central tube with a spacer in between to allow room for the feed flow, and then by rolling the envelopes such that the spiral is formed. At the outlet end of each spiral, an antitelescope device is placed to prevent the pressure of the liquid from deforming the membrane shape.
When we talk about membrane configurations, we can talk about what is referred to as dead end and cross flow. And a few of you were on the seminar that Dr. Tarabara had organized on Monday, and you saw that there talked about cross flow and there's slight modification on how they were accomplishing the cross flow. But with cross flow, with dead end, this is a typical filtration that you would do, actually, coffee filter. Water flows in one direction. And with a coffee filter, you're using gravity as for your pressure. You've got hydrostatic pressure. And the water flow and our pressure are in the exact same direction. And if you've done any sort of filtration, your particles collect on the filter, and your filtrate or your permeate flows through that filter. So that's a dead end. Cross flow, here's our membrane surface right here. Pressure is perpendicular to the surface. The feed is parallel to the surface. We still have particles, material collecting on that surface, and the permeate is perpendicular to the feed. And here's our concentrate. So our feed and our concentrate are parallel to one another. Our permeate is perpendicular to that. It's just another image of a spiral wound membrane, just to give you a size of these. So typically the diameter of these membranes ranges from about 0.1 to 0.46, so half a meter in diameter, up to almost a half a meter in diameter. Most common is about 0.2 meters, which is about 8 inches in diameter. So this spiral wound membrane is about 8 inches, roughly 8 inches in diameter. And the length of each element, so the length of each element is typically from about 1 to 1.5 meters, roughly 3 to 4 feet long. And then, as I mentioned, the permeate recovery per element typically is about 5 to 15% per element, which is why we need so many elements in order to achieve the recovery that we're desired. Now, the other thing to recognize is when we operate these as constant pressure or constant flow. We can't have both. Okay, if we have constant pressure, then over time, as that material deposits on the filter, your flow is going to decrease. If we operate at constant flow, then over time, the pressure that you need in order to push the flow through the membrane surface will increase. Operate at a constant pressure over time, Q will decrease with time. If we operate at constant flow, then pressure, so that pressure, the transmembrane pressure that we need in order to maintain that same flux will increase with time. And we'll talk more about this fouling layer that deposits on the membrane surface. These are tubular membranes. So here, this is a tubular membrane. So this is shown here as an outside-in configuration. The water flows from the outside. My filtration layer will deposit on the outside, water flows through, and this is my clean water. In a membrane bioreactor, which is what you see here, this is from a membrane bioreactor. These are the tubular membranes. They're fiber membranes. They're typically up to about 2 millimeters in diameter. So they're extremely small. And then the water is flowing from the reactor through the outside and then is being collected. Now we can also operate as an inside out, in which case these are ceramic membranes and the water flows. So this is our water to be treated. This would be operated in a cross flow mode. So this is the flow, this is our feed water. The permeate treated water flows through the membrane surface and out into a collection vessel, and the reject stream would flow out the other side. So this is our reject. The nice thing about ceramic membranes is they're extremely durable. You can dry these. You can take these out to a far remote location and turn on the system and operate it. Polymeric membranes need to be maintained wet. They're a little more difficult to just take out to such a remote location. This is the same thing. It is this type of a membrane. So if you have a backpacking membrane and it is a ceramic membrane, this is essentially what you have. One of the things you want to think, they do clog. So you want to clean these after because they clog. You also want to think about if you have a highly turbid water, you don't want to treat that directly. So for instance, back in 2014, when I went it was close to 100-mile backpacking trip down at Philmont with my son through Scouts. I was in charge of water treatment and nobody got sick, which was really cool. But there was one location downstream from the donkey paddock that there we actually treated the water through. I'm going to ask all of you. Okay. There is a stream. The stream is downstream from the donkey paddock. It is extremely turbid. How should I treat that water? And then I'll tell you what we did. Anybody want to venture to guess? And we did have ceramic filters. We could have boiled it. It would have taken a lot of time though, and a lot of energy. And we had not a lot of time to get to the next campsite. We could have let some of it settle. That would have taken some time too. We actually did some of it when we had time at night. We actually pre-filtered it through fabric filters. So we just made filters out of handkerchief type material that we had brought specifically for that purpose. So we pre-filtered it through the fabric filter, then filtered it through the ceramic filters, then added the chlorine tablets. When we were in the higher country and we were treating spring water, typically we then just filtered it through the ceramic filters. It was sufficient because it was both spring water and it was the high country, so there was less potential for contamination. But downstream of the Donkey paddock, we needed to make sure that we didn't clog the filters because of the turbidity, removed as much of the bacteria and viruses that we could on the ceramic filters, and then also treated with chlorination to ensure that we killed everything else. And we made sure that when we chlorinated, we let that water stand for the requisite 3 hours to try and make sure that we got the CT needed to disinfect. Just some applications of membrane filtration. You can take raw water and directly filter it through a membrane filter. This is done in Marquette. So Marquette has a membrane filtration system. I believe it was one of the first surface water membrane filtration systems in, well, Monroe was Marquette, I believe, was the first. The Mackinac Island also has membrane filtration now. One of the nice things about membrane filtration, especially pertinent to Marquette, is there's roughly 15,000 people on the island per day during the summer. And those people are on the island, they're eating, they're drinking, water's being consumed, so there needs to be sufficient water produced for that population. In the middle of winter, there may be less than 400 people on that island. So you need to have a plant. Think about this with your design. You need a plant that operates as effectively for those 400 people in the middle of winter to that 15,000 that are on the island in the summertime. It's quite the challenge. So both water and wastewater treatment plants have to operate with that kind of variability in flow. You can also use it for softening. In this case, there is in the second one, you have a softening step first, and then a membrane filter for further softening. This here is a direct filtration system. You're applying some coagulant, you've got some flocculation. Notice there isn't sedimentation. So this is again used for pristine water supplies. If you have a large amount of sediment that's produced, that's going to clog the filter very quickly. In this case, this is essentially a conventional treatment plant here, followed by membrane filtration for further treatment. You can also combine it with reverse osmosis. So for instance, you can have a microfiltration system or an ultrafiltration system, followed by reverse osmosis for targeted removal of certain pollutants. So as I mentioned before, in terms of the operation, you're going to get a layer of particles depositing on that membrane filter. We refer to that as the fouling layer. We also talk about it. Filtration cake. It's a little more complicated. I'm not going to go into the difference between, but basically know you have material that's depositing, and that is going to inhibit flow. And that's why if we operate at constant pressure, the flow decreases over time, or if we operate at constant flow, we need to increase the pressure over time. We can also have scaling. This is different than fouling. This really is the result of exceeding the solubility layer. So here is our membrane surface. So water's flowing through that membrane surface. We have a concentrate on this side. So the water's becoming more concentrated. And then what we have here is we can have a concentration gradient develop on that membrane surface. That results in higher concentrations of more insoluble materials, and then they deposit on the surface. So you get these precipitates, and that results in scaling. So it's scaling like we've talked about before, but in this case, it's scaling on the membrane surface. That can be very, very difficult to remove. It often requires extensive cleaning to remove that scaling layer. You can also have precipitation. So for instance, if you have reduced iron and that iron is being oxidized, then what you can end up with is a membrane that looks like this. So what's happened is that iron has oxidized from Fe2 plus to Fe3 plus, precipitated out as FeOH3. And you can probably imagine getting flow through that membrane is extremely difficult. When about 20 years ago, membrane filters were put in Chelsea, they didn't put in an iron treatment system. And within a few weeks, the membranes all looked like this. They then had to go back in, retrofit the plant in order to remove iron prior to filtration in order to prevent this. The other problem that we have is what's referred to as biofouling. And here what happens is you get microorganisms that attach to the membrane surface. Those microorganisms colonize the surface. They grow. They can release what we refer to as extracellular polymeric substances that coats the membrane surface. And as you can imagine, getting flow through that membrane becomes increasingly difficult. So because of all of this, in many cases, we pre-treat the water prior to feeding it on to the membrane or into the membrane. So we can add anti-scalants. So these are chemicals that are used to inhibit precipitation or crystal growth, to keep the chemicals that would precipitate in solution. So they could also sequestration agents, again, to keep these chemicals in solution. We can pre-filter. So we saw that with, for instance, with the RO, where there was a membrane filter, perhaps a microfiltration process before the reverse osmosis system, so that you're filtering out those particles prior to the RO unit. So you're minimizing fouling on the membrane unit. You can also add sulfuric acid to adjust the pH or caustic soda to adjust the pH. And here what you're looking at doing is changing the solubility. So you're trying to make whatever is precipitating, you want to prevent that precipitation. The other thing is, which isn't here, is disinfection. And as Austin just mentioned, here, what you're looking at doing is you're trying to kill the microorganisms to prevent excessive biofilm accumulation on the filter itself. So you're trying to prevent that biofilm growth. It's one of the reasons in the engineering building, if you go to the lab, there's the DI water and there's the regular tap water. You don't drink the DI water. And it's because of the chemical disinfectants. They used to use formaldehyde. I'm not sure if they're still using it, but they disinfect in order to prevent biofilm growth on the membrane itself. And then finally, I mentioned cleaning. Fouling will occur. It's almost inevitable. And so once the fouling occurs, then you need to clean the membrane, and that is typically done with acids or bases, or in some cases, a combination of both. And then you also may, again, disinfect to prevent biological fouling. And finally, the water that you're producing, especially if you're using reverse osmosis or nanofiltration, is essentially devoid of minerals. So I showed you the images from the pipes in some of the residence halls. Once that water is passed through the RO, there's essentially no minerals in it. It will typically have a low pH, as the alkalinity is also removed. The water is highly corrosive. So typically what you need to do is add a base. You want to add alkalinity in many cases and a corrosion inhibitor. Also, if you can, you have an RO unit, for instance, a below the sink RO unit at home, you want to use plastic piping. And if we could be in the engineering building and we could actually go look at the RO system, you would see that the RO water is all transported through the building with plastic piping because of the challenges related to the corrosivity of that water. The other challenge is, what do we do with this concentrate? It has a high total dissolved solids. We potentially can discharge it to a municipal sewer, but we need to be very careful with that, because if we change the salinity of our water, that has an impact on microbial growth. If we're using activated sludge or trickling filters or etc., oxidation ditches, it's going to affect the microorganisms. We can look at ocean discharge, but again, we have to be very, very careful, because if we discharge too close to the surface, we can actually change the salinity of the water in the estuary, which then impacts negatively the aquatic ecosystem. And in some cases, new RO systems have actually been banned because, or a moratorium placed on new facilities because of this impact on estuary ecosystems. And then lastly, we can look at deep well injection. So hopefully that gives you some sense of membrane systems